Hello and welcome. Today we're going to do one more example of separation of variables to find a PDE solution. And this one's going to be a little bit more advanced, just a little bit. So let's see what's going on here. Okay, so let's talk about, let's imagine a one-dimensional domain that's going to be 0 to L length. Okay, we'll just do abstract here. We won't pick any specific numbers. Okay, and we're going to imagine this domain is a one-dimensional lake. Think of it as a body of water that's long and can be at least conceptualized as a body of lake. And then consider a pollutant in the lake. That diffuses with diffusivity D. Okay. Furthermore, we're going to say that we're going to assume that this pollutant decays over time. It decays over time. It decays over time at exponentially at a rate alpha per density of material of the pollutant. So what do I mean by a U density? So we're going to let U of x comma t be that density. Okay. And we're going to assume the lake is zero flux at the endpoints. Okay, so our one-dimensional lake is zero flux, and that means U of x at 0 comma t is equal to 0 is equal to U sub x at L comma t. Okay, so our PDE can be written as follows. It's the time derivative is equal to d times the second spatial derivative. That's the diffusion of material in the lake. And there's going to be a minus alpha u. All right, so this is diffusion. Here is, of course, the dynamics. Okay, and then here, of course, is that exponential decay. So there we go. Right, those are our pieces to our differential equation. So, of course, right here, these two would be standard diffusion. And then, of course, this is this extra, or what I would call interesting dynamics. So this is an additional term that's added to the thing to make it maybe a little bit more interesting. So clearly there's going to be multiple things going on. Both diffusion, of course, spreads out stuff over time, and of course exponential decline, some sort of decay will take stuff away. Maybe this pollutant oxidizes or goes through some sort of reaction, and it eliminates from the system entirely. Okay, so our initial condition is going to be U of x comma 0, and it's going to be equal to 1 plus cosine of 2 pi over Lx. Right, if I were to make a little graph of that, it would look like 2, and it would go all the way down to 0 there at the middle of the lake. That would be L over 2. And would go back up and get to 2 there. okay? And its mean level of pollutant throughout the whole lake would be just 1 throughout the whole lake. That goes from 0 all the way to L. So let's now figure out what's going on. So one question I have, though, is will U at L over 2 in the middle of our lake ever reach 1/4? Okay, so we can see right now, if I actually look at the curve, it's below 1/4. So 1/4 would be, of course, at L over 2, 1/4 would be right there. And there, I'll put that blue line. That's 1/4. Right, so we expect from diffusion, we expect, of course, to see flux going in. Diffusion should push more and more of that pollutant into that zone there. But there's also this exponential decline. So we expect over time, all of the pollution will eventually decay out of the system. So we want to know if at some point in the middle will it reach 1/2. So clearly there's a push-pull going on here. Diffusion's adding stuff to the middle of the lake, and decay is taking away stuff. So we don't know what the answer is going to be. All right, so let's start with separation of variables. Let's do it. So we have ut is equal to duxx minus alpha u. All right, so we're going to take u is equal to p of x times q of t. And then, of course, we're going to plug in. So we're going to get p times q prime is equal to d times q times p double prime minus alpha p times q. Right, so now, of course, we're going to separate. So we can do that by just dividing everything by d pq, like that. I like to divide the whole d times pq, and we're going to get this. Sorry, undo. Okay. We're going to get q prime over dq equals d times p double prime over p minus alpha times 1, because both of them are going to cancel there. Okay. Again, I think it's actually better to try to change the equation a bit. This alpha term, I want to actually move that over to the other side. So I'm going to do that. That's going to be q prime over dq plus alpha, and that's going to equal I just found out I made a mistake here. So the d is gone there, of course. So the p double prime over p. Right. So remember, this is a function of t, and here this is of x only. So of course, two functions that are equal to each other but are of different independent variables, they must be equal to a constant. We don't know what those constants are. It could be more than one constant, and of course we'll find out that it is. Okay, so let's now solve this problem. We have an eigenfunction problem. So recall we have no flux boundary conditions, and we have a p double prime is equal to lambda p, with p prime of 0 equals p prime of L is equal to 0. We of course know these eigens. This is a very familiar eigenfunction problem. It's a very standard eigenfunction problem. It has solutions Pn of x is equal to cosine of n pi over Lx. And we have the lambda n is going to be equal to negative n pi over L quantity squared. And this is for n is equal to 0, 1, 2, 3, 4, and so on up forever. Notice that the n equals 0. That case is special. Lambda is equal to 0. And that p0 of x is just going to be 1, the constant. Okay, so we have our eigenfunctions right there. We box those up. Now, of course, we move on to talk about the time equation. So we have this now. Our lambda n's, we have negative n pi over L quantity squared, and that is for n equals 0, 1, 2, 3, and so on and so forth. And now we have the time equation, which was q prime over q plus alpha is equal to the lambda. So this will be for lambda n, that'll be equal to negative n pi over L quantity squared. All right, so from here, it's best to now move the alpha back over. So we're going to get q prime n is equal to negative n pi over L quantity squared minus alpha, that whole thing there, times, oh, we forgot our d. I need to remember that there has to be a d there. So I'll just put a d right there. That's good. Right, so all of our parameters seem to be showing up in this. So, of course, this is a function of time here. This, of course, has exponential solutions. Okay, these exponential solutions look like this. Qn of t equals e times an, that's our free parameter, negative times d of n pi over L quantity squared plus alpha times t. Okay, great. Now we can, of course, put Pn and Qn together, and we're going to get Un of x comma t is equal to An. Well, hold on, let me back up here a little bit. We'll just put all of them together like this. We'll just say u of x comma t is going to be equal to the sum n starts at 0 and goes up to forever times an e to the negative d n pi over L quantity squared plus alpha times t times cosine of n pi over L x. Right, so this right here is our general solution. It should be noted, though, we can write it in a slightly different way. We can write it with the n equals 0 term out of the sum, like this. And that might be a little easier to see how this all works. So we have an a0 e to the negative d times alpha t plus the sum, n starts at 1 now and goes up to forever, of e to the negative d times n pi over L quantity squared plus alpha times t, all times cosine of n pi over L x. Okay, what I like to see here is that this, of course, is that constant term. It's constant in space term. All right, so what we want to do now is look at that initial condition, which is u of x comma 0 is equal to 1 plus cosine 2 pi over L x. So that has to equal a naught plus, oh, sorry, I forgot my an there. I'll put the an in the sum above. Sum n equals 1 to infinity an cosine of n pi over L x. It's pretty clear that a naught has to be 1. And we can also see that a2 has to be 1 as well. Okay? But then an equals 0 otherwise. i.e. for the n's not equal to 0 and 2. Okay, so we can put that all together now. I'll put it on a new page now, which is going to be, so our u solution, our final solution is going to be e to the negative d times alpha t plus e to the negative d times 2 pi over L quantity squared plus alpha times t times cosine of 2 pi over Lx. So that's our solution. So this is our final answer. Okay, so we had that follow-up question though, which is, does u of x at L over 2 comma t ever equal 1/4? All right, remember that our initial solution looks like this a little bit. So this is the initial condition. Starts at 2. At the very edges of this one-dimensional lake. And I want to know at 1/4, will the at L over 2, will it ever get there? Well, we can just plug in x equals L over 2. Let's find out. We're going to get u of x comma t is equal to e to the negative d times alpha t plus, now of course cosine of 2 pi over L times L over 2, what's that going to be equal to? That's going to of course be equal to cosine of pi, because of course right here you have the L's cancel and the 2's cancel like that, which is going to be equal to -1. So what we have to write here then is we're going to write a negative e to the negative d times 2 pi over L quantity squared plus alpha times t. All right, so from here, we're going to have to now look at this and see if we can figure out if it will ever reach 1/4. So we won't be able to answer this without plotting a graph of it. Let's see if we can do some sort of analysis of this curve to see if we can come up with some answer here. So first off, if I look, oh, sorry, I should also write here that this is u at L over 2. We actually have to plug that in for x. So u of L over 2, if we plug in 0, of course we're going to get 0, all right? So we're starting from nothing, and we're going to eventually increase a little bit. We also know that if I take the limit as t goes to infinity of u of L over 2 comma t, that should also go to 0. We also know that u can never be less than 0. That could never be less than 0. This decays here. This decays more rapidly than this one right here. Okay, because of that, it should be that so the curve should look something like this, the graph. So this is u at L over 2 comma t. It should probably look something like this. as a function of time, right? So the question is, at its peak value, what is that peak value? Let's see if we can figure that out. The best way to do that is to use calculus to find a way. So we'll take the derivative now. With respect to time. And we should be able to get negative d alpha times e to the negative d alpha t plus d times 2 pi over L quantity squared plus alpha times e times all that over again times t. And now we're going to set that equal to 0. And we're going to have this. So for simple notation, let me just call that capital X. And that'll just make our notation a little bit simpler. This way I don't have to keep writing that big expression. So what I have here is now an equation that says d times alpha, e times negative d times alpha t is equal to x e to the negative x times t. All right. Well, we should be able to now handle this a little bit better and write this as d alpha over x is equal to e to the d alpha over times t all over e to the x times t. All right, and that's just using exponent laws and whatnot. We can write this a little further and call it e to the d alpha minus x t. We know that d alpha is smaller than x. Okay, we know that's true. So this should be decaying. Okay. And so what we can do now, of course, is take the logarithm. Because this is negative, though, we can actually flip it around. Natural log of x over d alpha. And that's going to equal x minus d alpha times time. So our special time for our peak value is going to equal natural log of x over d alpha all over x minus d alpha. All right, so what we do here, of course, is, so this is the time, this is our peak time. What you can do, of course, is plug this in to find out if u at L over 2 comma t star is greater than 1/4. Of course, here you're going to have to, pick. We're going to have to pick D, pick alpha, pick L, all of those things, and then we can assess how these parameters might affect the situation. So it's not clear immediately. We can't prove this outright, but the idea here is that this is eminently doable. Clearly what happens, though, is that what we can tell from this, though, is most certainly that a peak does occur at x equals L over 2 before it starts decaying again. So you are getting some amount of diffusion towards the middle of the lake, and then there's going to be some slower some sort of exponential decline going down as you go down. So there will be always a little bit of decay. There'll always be a little bit of diffusion inward before the decay takes over. Okay, anyway, I hope this problem gives you a good idea of how PDE solutions work, how you can analyze them and study them to answer specific questions, as well as how to use separation of variables to find solutions. I hope you enjoyed it. Thanks very much.